All right, let's go ahead and get started. Looks like we already got a pretty good number of attendees who've joined the session today, with more flowing in as I speak. So yeah, I'm going to go ahead and quickly kick off the session so we have plenty of time for questions at the end. So first of all, let me start off by introducing myself, and I guess I'll ask if those of you who are joining can remain on mute till the end, until we get to questions. That'd be great. So my name is Jeff Mealiffe. I'm a principal product manager at Microsoft. I've been with Microsoft for a little over 22 years. And I've been working on Exchange or around Exchange pretty much the entire time. So I'm super excited that MEC is back yet again. Wish it was in person. Wish we could go hang out after the session and get a drink, but we'll have to wait for the next time MEC comes back. So in my current role, I'm part of the Microsoft 365 routing plane team. And you can think of that team as the group that's responsible for taking a client request from the internet, from wherever it's coming from, and getting it where it needs to go. So that's with some level of responsibility all the way up through the networking stack and up through the proxy layer that sits at the edge of our network, that's responsible for figuring out how to direct requests. We don't own all of the optical connections sitting in data centers that connect us to internet service providers. We rely on our partners in the Azure networking team to deliver a lot of that infrastructure that makes up the Azure network. We are probably safe for me to say the largest consumer of that Azure network in terms of delivering the Exchange Online service, or the substrate more broadly. So today we're talking about an insider's view of Exchange Online connectivity. I've been with this team for a number of years, and I'd like to think of myself as an insider in this space. So what I'd like to do is spend some time going through some of what I think is fairly cool tech that we've built that we use to deliver Exchange Online at fairly significant scale, and I'll give you an example of that scale in a moment when I talk through some of the numbers that we use primarily to focus on availability and performance. Those are really the two things that we're most concerned with when we think about innovating in this technology space. Obviously, availability is key. We're held to an SLA. We want to make sure that we're doing whatever we possibly can to ensure that Exchange Online is delivering a level of service that goes ideally above and beyond what you might have been able to provide with an on-premises solution with legacy Exchange, or in a modern Exchange deployment on premises. We're very much focused on ensuring that we are as available as possible, and connectivity has a big piece to play in that. I'll go into some detail on that in a moment. And then performance also comes into play. When you think about consuming a service over the internet, a cloud service that you don't directly control, where you don't directly control the end-to-end connectivity path anymore, that connectivity path has a fairly significant impact on performance. And there are certain limits in terms of what we can do to try and improve performance from that perspective. But at the same time, there's quite a bit of innovation that we can do both in the product directly, both client and server side, as well as the path that those packets take between your infrastructure and the edge of our network, as well as within our network, to try and make improvements and reduce latency and deliver the best experience possible. And to that point, there are things that we do, and this is all about the second bullet point on the slide here. There are things that we do, architecturally within the design of our service, where we're making some expectations that or some assumptions that our customers are going to kind of help us out with some of these investments, that we're going to make changes within our infrastructure that, as an example, push our cloud closer and closer to our end users. In order for you to take advantage of that, there are some things you need to be aware of in the way that you deploy your infrastructure and the way you operate your infrastructure. Without a little bit of help from our customers, a lot of these investments that we make to try and drive availability and performance enhancements, may not be nearly as effective. So we'll talk through some of that as well today. Give some specific examples of what I'm referring to. So and you know, I've already kind of touched on the content in this slide, but I really love this slide because I think it drives the point home. There are really two things that drive a great user experience for cloud services. For SaaS services specifically, where Exchange Online is certainly one of the biggest and the one we're talking about today. Great product. You know, Exchange has a long legacy of being a great product and just getting better over time, and optimal user connectivity. So we're gonna talk about that latter half today, and a lot of the other sessions at MAC really go into more detail about the great product aspect. So let's talk a little bit about scale. And for those of you who haven't seen it, the image that's the globe image that's you know, showing behind this slide is actually taken from a really cool site that the Azure team just put up recently. That's sort of a visualization of all the Azure infrastructure around the world. This has it just kind of filtered down to the wide area network links and the network pops that Azure networking operates and we take advantage of as a service. But there's a link at the bottom of the screen. Feel free to to go check it out. You can overlay all the different types of Azure infrastructure on the map and browse through it. It's super cool. So thinking about Exchange Online and the substrate specifically, we operate on the order of 300 data center locations around the world. It's a fairly significant number, and it continues to grow. Every time I do a talk of this type and go to update this slide, I'm always amazed at how these numbers change, particularly the last one that I'll talk about in a moment. Our team operates on the order of about 40,000 network devices. When I'm talking about, there are things like the switches that are actually effectively routers that sit at the top of all of our racks across Exchange Online, load balancers that handle distributing traffic amongst cafe servers, the front end servers that terminate inbound requests. So fairly significant number of devices that we manage as code effectively. And operate as on-call engineers within the service. I'm actually technically on call this week. I was thankfully able to trade today's on-call day for another day next week, because it would have been great to get paged in the middle of this session. But yeah, as on-call engineers, we're responsible for all of that infrastructure, keeping it up and running, and quickly responding to any issues that are caught. We have around 300 network POPs, points of presence around the world, and these are places where we exchange traffic with internet service providers. In some cases, there's certain direct connectivity types, primarily used for Azure, but occasionally used for our SaaS services, things like Express. So we have those globally distributed. In some cases, we actually are pushing content distribution facilities out to those network POPs as well, to try and get things like static content as close as possible to our end users. Things that where we're not carrying customer data, but can take advantage of that breadth of deployment to get that content out as close as possible to the user. And then this last number just kind of blows my mind. So we do about 3.5 trillion routing plane requests per day. So this is a combination of inbound requests from end users that are hitting our front end servers. Cases where in some cases we will be proxying those connections to an additional cafe. We do that as a to help with performance in some cases, where we're taking a request in at a location that's as close as possible to the end user, and their mailbox happens to be in a different region. So in some cases we'll do a multi-cafe hop. So that adds to those numbers, and then this also reflects cases where we have inbound requests using the substrate services internally within Microsoft, where some of those requests hit our front end, hit cafe, and need to be directed to the appropriate Exchange Online backend to get to the data that's being asked for. So fairly large number. The last time I did a talk where the slide was presented was, I want to say, a little bit over a year ago, and that number was 2.5 trillion, or actually slightly under 2.5 trillion. So it's grown by about a trillion requests since then, which is a significant growth rate. So large service. we're super proud of the infrastructure that we built, and the fact that we can, deliver the availability that we have. And then before I get into the nitty gritty about what I want to talk to today, I did want to level set on terminology, and I think this is super important. We use these concepts of first mile, middle mile, and last mile all the time at Microsoft, and we just kind of throw out these terms like everyone understands what we mean. Many of the slides that I'm going to talk to in a few minutes use these terms, so I want to make sure everyone understands what I'm referring to. So when we think about components of connectivity, the first mile, this is really the portion of the path between end user and service that Microsoft is fully responsible for. We own the first mile. So this is our internal wide area network that connects all of our data centers, basically everything up to what we refer to as the peering router. And the peering router would be that device that sits in one of those network points of presence that interconnects with internet service providers or some sort of network provider that's handing off traffic to us. Could be a local ISP, could be a transit provider that's taking traffic long distances. Lots of different types of providers in that space, but effectively up to the peering router, that is the first mile. That's all Microsoft. The middle mile is all about getting packets from the last mile to the first mile. So that's typically the realm of an internet service provider. There are other types of solutions in this space. You could think of some of those secure web gateway types of solutions that might be handling traffic. We would consider those to also be middle mile providers because again, they're taking traffic and handing it off to Microsoft at a peering point. So they sit in the middle mile, but primarily we think of ISPs as being that middle mile. And then the last mile is really your infrastructure. So this can come in many forms. Obviously, with the advent of hybrid work and work from anywhere, which I'm taking full advantage of right now, the small office, home office, last mile is becoming much more important these days. We obviously have been dealing with the mobile last mile for quite some time with LTE and 5G connected devices that we carry around in our pockets all the time, as well as with various connectivity for laptops and other things. And then we have the most complex of the last mile solutions being the enterprise last mile. And that's where we run into a lot of challenges trying to align best practices that we'll talk through in a few minutes. So last mile, middle mile, first mile. Really, the only thing to keep in mind here is last mile is all about kind of customer-owned infrastructure. First mile is about that Microsoft piece that we deliver. So next two things I want to go through: traffic management and detection and recovery. Traffic management is really all about how Microsoft manages that incoming traffic to our endpoints, and what we do to make sure that we are handling it with high availability and the best possible performance. So when we think about the design principles that go into to traffic management, a lot of what we do at Microsoft, kind of regardless of the domain that we're talking about, we like building systems that are active, where there are two ways to make something happen, both of which are always operational. So if one goes down, obviously we have another side of things that can take over and handle the load. You can think about an Exchange DAG as being an example of this, where you have mailbox servers that are handling active copies of a database. At the same time, they're also handling replication with passive copies of a database. And ideally, you have things spread out where you have active and passive copies that are sort of equally balanced across mailbox servers. That's effectively an active solution where you have some active mailboxes running on all those mailbox servers at all times. So that the system is capable of performing. Same thing applies in traffic management. We always want to have two or more paths that are active that we can rely on. So we want them to be as independent as possible. And that comes in a number of flavors. It could mean that they're running different types of infrastructure. They have different implementations. They sit on different platforms. From a physical networking perspective, you could think of this as WAN links that that are provided by different lease line providers that are never in the same conduit in the same location to avoid a backhoe taking out both of them simultaneously. So operational independence is important. From a sizing perspective, again, you want to make sure that everything is capable of running on a single path, and so you want to make sure that each one of those paths is sized to handle 100% of the load. Anytime you're building a complex system, there's going to be a bunch of components that depend on each other. So it's really important to have a good contract between all of those dependencies. You want to minimize dependencies as much as possible, obviously, but where you have to take them, you have to have a very well-defined contract that helps you understand that SLA and kind of estimate what the probability is of failure in those spaces. So those are sort of the high-level design principles that we use around traffic management. So taking this specifically to Exchange Online, what do we do in this space? So we try and do the very best job we can, and this is again a space where we're constantly innovating to direct inbound requests to an endpoint that is optimal at that point in time. Where optimal has some different definitions. We're highly interested in minimizing latency, and so we're going to try and handle that request in a location that is as close as possible to our perception of where that request originated. I'll talk about the implications of that perception in a moment. We're going to try and mitigate any sort of availability issues that are occurring with a given endpoint. What that means is, obviously everything fails, right? We experience many failures every day in our service, and these are the kind of things that we often are handling at like the level of a rack. So there might be some sort of a software issue or a hardware issue that occurs within a rack, and we'll just switch that entire rack out. We want to make sure that from a traffic management perspective that we're no longer sending traffic to that rack, and that requests are getting directed appropriately as a result of that. We also want to manage load issues. So there's certainly the possibility that we could be experiencing high load in a given data center location where we're handling these inbound requests, and that's bad for us and bad for you, right? High load potentially means increased latency, and so we're going to try and spread things out as much as possible. Obviously, the farther away we handle a request from the user, the higher the latency is, and we're potentially going to impact performance as a result. But again, we have to kind of manage that with the possibility that the high load is also going to impact latency and give you potentially a worse impact. So we have systems that are running behind the scenes that constantly monitor load at the cafe layer of our system and spread things out as needed, or we refer to it as shedding load to a different location. And we're also interested in reducing costs, right? When we think about the way in which we're going to carry traffic across our wide area network, or the location in which we peer with an ISP to take traffic, or the ISP that that's used to transit the traffic back to you, all of these things have costs associated with them, and there's a fairly complex equation that comes into play in terms of what the actual cost of handling a request is going to be. We tend to look at these things not at the level of an individual request, but more at a macro level, and we're very interested in finding new and innovative ways to try and reduce the cost of operating the system. We have a very expensive network bill for operating a service at this scale, and so we do what we can to try and manage that. And that means we can offer the SaaS service that we provide today, at the cost that we do. So generally, traffic management for a SaaS service, not Exchange specifically, but in general for SaaS services, traffic management is based on DNS. So you make a DNS request for a given endpoint. Your Outlook client will go and connect to outlook.office365.com, and you're going to get back one or more IP addresses as a result that your client will then go and connect to. Obviously, because we have some control over that infrastructure that is going to, do that translation between name and IP address, and those IP addresses represent discrete pieces of our infrastructure that you're going to connect to, that's the place where we can have the biggest impact on where that request is going to land. So that's why traffic management happens via DNS. And we do this in two different ways, going back to that design principle of two hot paths. So we use Azure Traffic Manager, which you all can use as well. That's a service that's available in the IaaS options that exist within the Azure cloud. Azure Traffic Manager is a traffic management solution that will allow you to create profiles and balance inbound load based on specific business requirements that you have. And then we also have a component called ACDC, which is Anycast DNS on Cafe. And we're effectively using these. You could think about it sort of as a 50-50 split when you make a DNS request for one of our namespaces. Some of those requests are going to be handled by ATM, and some of them are going to be handled by ACDC. In general, you're going to get effectively the same result, but we want to make sure that if there is an ACDC outage or if there is an ATM outage, that one of those solutions can take over. Both of those solutions use the inbound DNS request as a signal of where the end user is. And this is why your DNS infrastructure is actually really critical in terms of ensuring a good end user experience. And we've said for many years, we want you to get your traffic to the internet and then onto Microsoft as close as possible to the end user. And there's usually a little caveat at the end of that says with matching DNS resolution. This is where that comes into play. If your DNS resolution is happening, as an example, halfway around the globe from where you're getting your traffic onto the internet, when we do this traffic management process, when we go and figure out what location the end user is coming from, we're going to see that DNS request originating from halfway around the globe, and we're going to send that request to a cafe or client access front end. Apologies to those of you who were commenting in chat that I didn't define that acronym. That's close to your DNS infrastructure, not close to the end user. And that's going to add a whole bunch of latency, and the end user is going to experience a whole bunch of pain as a result. So having DNS infrastructure that's at least regionally close to your end users, and really more specifically to where their traffic is hitting the internet, is really critical for traffic management. And this, again, applies to Exchange Online. It also applies to other SaaS solutions as well. I mean, frankly, it applies to, at your home when you're using something like Netflix, right? Netflix uses uses DNS as a clue to understand where you are, so they can, filter their catalog to, to what's licensed in your region. Same concept. DNS is really critical. There is a DNS extension, EDNS client subnet, that can help here in some scenarios where there's some additional hints effectively that are provided through DNS requests about the actual location of the end user that initiated the request. Doesn't work in all cases, so can't rely on it 100%. But the message there about EDNS client subnet is, if that's something that your DNS infrastructure supports that you haven't enabled, this would be a great reason to enable that and begin sending that, those additional hints to us that we can use within our traffic management policies. The other thing to be aware of, public DNS resolvers. So this would be things like, Google DNS or Cloudflare DNS, people using 8.8.8.8 or 1.1.1.1 for DNS resolution. When you do that to access a SaaS service, you're basically saying, I'm now going to rely on whoever that DNS provider is and their infrastructure and the breadth of their deployment to define where my end users are. Because what it means is Microsoft is going to see those DNS requests originating from from those public DNS forwarders or those public DNS resolvers, wherever that public DNS provider has their infrastructure. Example of this, let's say hypothetically, I'm not going to throw one of those providers under the bus. We'll just say, Mealiffe DNS provides this service, and I only have infrastructure in the U.S. and Dubai. So I have some end users who want to access Exchange Online. They're in Australia. Their DNS requests are going to end up, getting forwarded to whatever's closest, typically from an anycast perspective, so like least hops on the network, either to the US or to Dubai. And Microsoft is going to assume, based on where that request ended up, that my end user is either in the US or Dubai, not Australia. So we make a bad traffic management choice as a result. Public DNS resolvers are generally okay. You just need to understand what you're getting into and pick one that has good breadth of deployment. You may find that there are occasionally locations for, those of you who have large enterprises out there that don't work so well in this. And those are cases where you might want to, not use a public DNS resolver and consider deploying your own infrastructure that's closer. All right. So just to reiterate, get your traffic onto the internet as close as possible to the end user. We do something called cold potato routing, where we will grab traffic onto our network as close as possible, where it hits the internet, and we'll optimally route it where it needs to go on our network. Tends to be much better than sort of a hot potato scenario where we'll try and keep it on the internet as long as possible, and take it close to the infrastructure that's going to process it. We want it on our network so we can have more impact on a good experience, both from an availability and a performance perspective. And then I touched on the DNS pieces, so won't reiterate that. So detection and recovery. This is about Microsoft understanding when things go wrong. Again, everything fails. We just have to deal with that. So we use two forms of signals to understand when things fail: passive and active signals. Active signals are, sort of those obvious, ongoing probes. You can imagine any online service, and for those of you who have, enterprise deployments of your own, you're probably using something similar where there's some sort of service out there somewhere that's constantly sending inbound requests in to understand whether or not they can reach their destination, and perhaps monitoring some of the performance aspects of the requests so that you can, trend over time and try and detect and resolve problems of a latency nature. So active signals, always kind of probing and looking for issues actively. Passive signals are different. Passive signals are things that are based on organic user traffic, as an example. So we know that we're generally going to be receiving traffic in a given location at all times, as long as things are working properly. We never run into a situation where we don't receive any traffic. A passive signal, an example of that would be not seeing any traffic. There are also scenarios where we have telemetry that's more passive in nature, not sort of this active probing, and just more sort of behind the scenes telemetry that's collected on an ongoing basis to see how the system is operating. So we have lots and lots of signals flowing in to Microsoft of different forms. I'll talk about a couple of the specific ones in a moment. And we use these in real time to detect issues and quickly respond to them. The way we respond to them is typically in an automated way, because the moment we talk about bringing an engineer like myself into the fray to try and resolve something, it's typically going to take longer than an automated recovery would. If I'm jumping in, I'm going to need to go figure out all the context of what's going on, understand how the system is operating broadly, and try and figure out, kind of from a basic troubleshooting perspective, how to resolve the issue. An automated recovery can do that, much more quickly, assuming that it's programmed to do so. So at the first mile on our side, we typically are handling recoveries by shifting to alternate endpoints. So from a DNS perspective, this would mean, as an example, Outlook.office365.com might stop responding with some certain set of IP addresses that represent, chunks of cafe capacity around the world, and instead, is shifting traffic elsewhere. We can also do recovery via BGP, and that means that essentially we're, shifting traffic that's going to particular IP addresses to different network points of presence. So we might stop advertising routes to Microsoft's network in one location, and that forces traffic to take a different path on the internet. Middle mile recovery. So we actually see, even though we don't own the middle mile, we actually have great visibility into middle mile problems. When you operate a network of the scale that we have, we have a lot of the traffic on the internet that comes to Microsoft and is coming to Exchange Online. And so, when there are these large scale outages, like the one in Canada, I think it was about a month ago, other similar issues that happen around the world, we very quickly see these. In fact, we get alerted on them, and in cases where we can actually do something about it, we do. And there's examples where, for ISPs that peer with us directly, we can, pull routes from one of those peers, which, depending on what specifically we're trying to do from a traffic engineering perspective, can force traffic to, go to hit Microsoft's network in a different location, and try and avoid, perhaps a hardware issue or a fiber issue. We can, shut ports down completely. Similar outcome. Some cases we're just reaching out to a network operations center. That tends to not generally result in a good real-time outcome, because those are slow conversations. But in some cases it's still valuable to have the conversation and let the ISP know that we're seeing a problem, in case they perhaps didn't notice. So from a best practices perspective, when we think about detection and recovery, we want to make sure that our customers are not doing anything funky with DNS behind the scenes. We do have cases where we've worked with customers who are effectively trying to pin the location that their traffic is hitting via DNS overrides. You could do this with something like the bind DNS resolver within your own infrastructure, where you can define something called a RPZ, response policy zone, that says, if I see a request for a given name, this is the IP address that I should use, as opposed to going out to Microsoft and saying, hey, Microsoft, translate that name for me to, the real answer. Avoid doing that, because that effectively means you're now kind of managing availability and performance for us, and all of what I described previously about what we do from a traffic management perspective to optimize your connectivity just kind of goes out the window. So that's a big no-no. Also, ideally, avoid locking down DNS. What I mean by this is we do run into cases where customers will lock down DNS to specific allowed zones, and those don't necessarily align perfectly with the namespaces that we publish on our list of required endpoints for Microsoft 365. What comes into play there is that in a failure mode, there may be scenarios where we start using a CNAME record in DNS or something like this that takes traffic sort of outside of the normal pattern that you might see in just regular day-to-day operation, where we've published that namespace is required, but because you didn't see it on your network at the the point in time that you kind of took a snapshot of what's needed to make things work, that you end up experiencing a failure where other customers would continue to be operational. So avoid locking down DNS where you can from that perspective. Obviously, keep proxy and firewall config up to date. That's something we've talked about forever. We publish the required namespaces and IPs at the link that's on the slide. And we also have a web service that can be used to automate the process of keeping that up to date. And then path diversity is quite critical. And we'll jump into that. So again, everything fails, including internet links. Wherever possible, we encourage our customers to use path diversity for their internet connectivity. Think about using multiple ISPs, right? If you have branch locations where you're relying on internet connectivity, a couple of commodity, potentially consumer level internet connections may make more sense than a single business class connection. Obviously, you'll have to evaluate what that looks like for your specific scenario, and what you get out of the SLA that's associated with business class connectivity. But it's very similar to the concept of JBOD for exchange storage, right? Multiple sort of cheaper solutions with the expectation that one of them can fail at any point in time may be a better choice than a single more expensive solution. So consider that, but also keep in mind that the benefit here is about expecting failure and handling it appropriately, and also when you have a single ISP, there are things that Microsoft can do at the first mile to try and help the ISP still get their traffic to Microsoft if there's a problem. But we still see cases where reliance on a single ISP results in your connectivity kind of getting pinned within that ISP's network and not being able to get out. Even though that ISP may have quite a bit of redundancy, quite a few locations where they peer with other providers as well as Microsoft. So multiple ISPs is a great way to go if you can. And I guess the only point that I didn't cover is this last one. So if you are trying to ensure that you have high availability from this path diversity perspective, you absolutely should be testing it on an ongoing basis. Make sure that that things work from a failover perspective, or if you can, use active-active. That doesn't always work if your if your backup is something like 5G, where you're you may not have all the bandwidth you need to operate active-active, and it's more of a sort of a worst case failover. But if you can do active-active, it's always going to be better. And last but not least, just kind of closing out the detection and recovery piece. So we actually operate an automated solution called DARE, the Detect, Alert, and Recover engine. It's used across Microsoft 365 by a lot of workloads within the suite, where we detect in an automated way that there are failures occurring to a given endpoint. And we do this via some signals that we receive, primarily footprint and NEL, that I'll network error logging that I'll talk about in the next slide. And in real time, we can effectively see for a given scope that we're beginning to see failures against a certain endpoint. Example of this might be for Comcast customers in the Atlanta metro region, they're having a problem reaching teams.microsoft.com. We can get that granular with this detection engine. And as a result of that granularity, we can then take some automated actions. The sort of most minimal automated action is, hey, let's go page an engineer. Let's go alert somebody that there's a problem. And that may be the right thing to do if it's a super scoped scenario like that, like I just described. There may not be much we can do from an automated perspective to help Comcast or some other ISP in the Atlanta metro, fix an issue. However, we can certainly reach out to our customers and let them know that there's a problem. And one of the things that DARE can do from that perspective is actually auto post to the service help dashboard. Some of you may have seen where we'll actually say that there's an issue with internet service provider connectivity in a given area. Those are actually targeted to customers where we actually see traffic coming through the network where we've detected a problem. We have a way to associate end user connectivity with a given ISP on an ongoing basis, and we use that to target those messages. Now, if we actually see a much wider scoped anomaly, so an example of this would be all requests that are going through the Azure Traffic Manager path to Exchange Online are failing. In that case, we will, in an automated way, fail that path and stop sending any requests to Azure Traffic Manager and use AC/DC, Anycast DNS on Cafe, for 100% of the load. We can also do this as an example between requests hitting Cafe or hitting Azure Front Door, which is used for some workloads for similar purposes to terminate a connection and send it where it needs to go on Microsoft's network. We can make those kind of shifts in an automated way as well. So this is a service that Exchange has built that has grown over the years to be a really critical service for providing availability across the service. So where does that signal come from? Two places. So Footprint is probably the biggest. Some of you are aware of Footprint. We've talked about it in kind of high level over the years, but think about this as Microsoft Office clients occasionally going and running, and when I say occasionally, I mean very rarely, going and making a small request out to a Microsoft endpoint and defining or gathering a couple of quick metrics like what the latency looks like, the path in some cases, and the latency of making a DNS request, and then pushing that back up to Microsoft in a privacy-sensitive way where we're not actually collecting any end user identifiable information associated with that. So we're not, as an example, collecting like the very specific IP addresses that are associated with these requests. We're masking them to a broader set of addresses. And doing this in a way that aligns with our trust principles and the statements that we make around how we manage data. So Footprint is sort of always running in the background, and while it may run very, very infrequently on a given user's workstation, because of the breadth of deployment that we have of clients, we actually get a lot of signal volume. So this is a very, very useful signal to us about what the reachability and performance of our network looks like. We have a doc that's out on the web at this link here on the slide that describes exactly kind of what this is, the data that's collected, and how it's used, in case you're curious. Network error logging is another solution that we have. This is built into Chromium. So if you're using the Edge browser, any other browser that's based on the Chromium renderer, there's a way that websites can push down a policy that says if there's any problem reaching this website or this websites that are at this namespace, send a report to this address. And as a result, we get things like feedback on DNS queries aren't working, or SSL certificates are improperly configured, or the connection is just being refused, and the upload endpoint for these reports is not on Microsoft's network. It's on a different provider's infrastructure, and so we can then sort of via a back path get this signal even when Microsoft's network is experiencing problems. So if you go look at some requests that come down from Exchange Online, you can see these NEL policies come down. So I'm going to very quickly flow through a couple of examples of ways in which we use some of that data to benefit you beyond sort of the traffic management discussion that I've already had, and then we'll jump into questions. So the Footprint data that we use, in case some of you are unaware of this, flows into the network connectivity health section of the Microsoft 365 Admin Center. And we use this information to essentially build a map of where we perceive your traffic to be coming from around the globe, and provide some feedback on how your connectivity is performing relative to other customers in similar areas and what you can do to improve it. And so we'll attempt to associate your traffic with these given locations. We'll provide insights on improvements that can be made, potentially with examples of the millisecond improvement on latency that could be achieved. And we provide a kind of an overall assessment score that feeds into the productivity score that you'll also see in the admin center. And this goes down again to individual branch locations where we detect traffic. You can customize those as well and give us some additional feedback on the IP addresses that are associated with your branches, and then we can do a better job of providing this feedback. We also have something called app connectivity monitoring, and this exists as part of the customer monitoring effort that we have in the admin center. This is also using Footprint, where we're able to help you understand the impact of service incidents that occur in our cloud on your end user connectivity. So this is really about availability And what we do here is overlay SHD postings with some visibility into those availability signals that Footprint is providing specific to your end users. So another great use of that Footprint data for you. We also have a new map, sort of our network health status map. This is not an authenticated scenario. This is available to the general public. And this is actually pulling in signal from the detection and recovery engine that I was referring to earlier, where we will actually reflect anomalies that we are seeing from an internet connectivity perspective around the world in real time. So you can get a sense of what the Microsoft perception is of end user connectivity kind of end to end. This is not really about first mile problems. This is about the end to end path and typically reflects problems that we see in the middle mile. So another cool visualization that's enabled by this telemetry. And then last but not least, we have a solution called Informed Network Routing. If you are a user of an SD-WAN platform, this is a feature that we have where we will actually exchange telemetry with that SD-WAN platform that can be used for near real-time adjustments to the path that your traffic takes to reach Microsoft to try and, again, improve performance on an ongoing basis. Yep, I don't need to go into depth on that. So quick summary and closing, and then we'll have a few minutes for questions. So for those of you who haven't seen our network connectivity principles, there's a link on the screen that'll take you to a great web page that goes through a lot of depth about these 4 principles. If you are interested in trying to improve your network connectivity for Microsoft 365 or really any SaaS solution, these are the 4 principles that we feel strongly will benefit you if you can adhere to these. I mentioned at the start, we do a bunch of work on our end to try and optimize things. We want you to kind of meet us in the middle. If you can align to these 4 principles, that's how you're going to set yourself up for success in the future. So last but not least, we're super focused on trying to help customers achieve better availability and perf. We're focused on transparency. We're focused on trying to achieve these things in a privacy sensitive way in terms of the telemetry that we're pulling in. And we're hopeful that what we're doing is actually helping end user experience, and I think we can see it from the data that we look at, and hopefully you notice it as well. So I will use the last 3 minutes that we've got for a couple of questions. If you want to post questions in chat, we can do that, or if you want to come off mute, feel free. It looks like most of the questions in chat have already been answered. It's a question about where the app-specific network performance page is. That's the app connectivity page. So customer monitoring is currently focused on large tenants. So it's basically kind of bounded by tenant size with a goal of eventually kind of expanding that. So think about it as kind of being in a, I don't know that we would call it necessarily a preview, but it's very much focused on large tenants at the moment, with a goal to broaden it. There's some good reasons for that. The signal quality is much better for things like that app connectivity monitoring when it is a large tenant. We can provide much more relevant feedback. Current guidance on using a forward proxy. So the way to think about that, this goes back to the principles of network connectivity that I pointed to. There are a set of endpoints for Microsoft 365 and Exchange Online specifically that we consider to be most important to optimize. And those are the ones where you want to bypass proxy. We created this taxonomy of optimize, allow, and default, where it's sort of a sliding scale of how critical they are to end user experience. So default you could think of as kind of being similar to just generic internet connectivity in terms of level of trust and what the way you should manage that on your network. So by all means, if you have proxy infrastructure in your organization, send the default traffic through that proxy. That makes perfect sense. Optimize is the other side of that, where we really want to avoid sending that through a proxy if at all possible. And then allow is sort of in the middle. There are scenarios where you may want that extra visibility for various reasons. You're going to have less impact on end user experience if you pass the allow traffic through the proxy. But again, if you can avoid it, you will see some benefit by avoiding it. What's the definition of a large tenant? Well, thousands of users, I think would be a good definition. Let's see. We've got Peter with his hand up. Peter, do you want to ask a question?
Yes, I want. Hi, Jeff.
Hey.
I think the answer was within your presentation, but still I want to ask that specific question. I work for a Microsoft partner. We do have customers, for instance, they have their tenant located in Europe. Let's say in Europe, we have 2,000 employees at that company. And in the Asia region, we have about 10,000 users for that same company. So they are working mostly, or their workers are mostly located in the China region. Are there any specific recommendations you have, or just use Microsoft 365 as it is with the typical internet outbreak from China? I know there are some documents available about doing it with a VPN connection, but still, what is your recommendation? How should we go further with such projects? And 21 Bionet is not the solution.
Yeah, understood. So for the scenario where you need to have, the collaboration experience of a single tenant worldwide, I totally get that the 21 Bionet solution doesn't make sense there. So for the connectivity egressing from China, in this forum, my answer will be, follow the documentation on that's published. There are some nuances to that I'd be more than happy to go into, offline with you. I just want to make sure that, that for the recording and for everyone else here who may not, be aware of all the nuances, we have some very specific documentation online that tries to help with this. Peter, if you want to follow up with me offline, Jeff at Microsoft.com, happy to set up a kind of a one-on-one discussion about that. But the basic answer there is if you follow the guidance that we have, you can generally achieve an acceptable level of performance. There are ways to further optimize it.
Okay, appreciate it. Thanks.
Sure. All right, we're already a couple minutes over. I'll go ahead and answer a couple more questions in the chat. Happy to hang on here for a couple extra, but want to make sure you get time to get to the next session. So let's see, how to use a network connectivity blade without activating location services. It's a GDPR thing. So you're referring, I presume, to the connectivity health section in the admin center. So you don't have to activate location to take full advantage of that of the feedback that's provided there. So by default, location detection is not enabled. And for those who are unaware of what I'm talking about, there's an option within that network connectivity health section to basically set a flag to turn a feature on that will push down a configuration setting to your end users' workstations that will detect fairly granular location. It's not going to be a way to identify the specific building that the user's in, but it's within a city we can get a sense of kind of where approximately that location is. That is not required to take advantage of it. So by default, we're just using kind of reverse IP databases to go associate the IP addresses that your traffic is originating from with your particular tenant in a particular location. If you have the ability to go configure those specific egress IP addresses on the location settings within that within the admin portal, where we're not doing as much guessing, that actually is a great way to take full advantage of that feedback without turning the location settings on, because then we will we won't be guessing and we won't be using some of those third-party reverse IP databases that are not super accurate in terms of location. So that's the kind of long-winded answer. Go configure egress IP addresses, and you can also configure internal LAN IP addresses as well, and that will help us understand backhauled traffic. So we can figure out internally within your network, that this traffic came from branch A, even though it egressed from data center B. So that's the way to do that. And then let's see what else. Guidance for optimizing hybrid or centralized mail transport environment for best connectivity and avoidance of performance delivery issues. I don't think we have any specific guidance around optimizing hybrid or CMT. I think the question there is really about the ingress traffic into your network that's generated by Microsoft, I'm guessing, because the egress connectivity in that kind of deployment would just align with our principles of network connectivity. Again, Microsoft is just going to use internet routing to get traffic to you in the most effective way possible, based on BGP and least hops. So not backhauling that traffic within a WAN, and instead publishing routes in the location where you've got that hybrid infrastructure would certainly be one optimization. Beyond that, I kind of struggle to come up with more suggestions, but yeah, that's kind of what we got there. Let's see, how to balance network connectivity concepts such as bypassing proxies against vendors offering SaaS solutions to protect O365 traffic. So that's a great question, and I think I'm going to answer that one, and then we'll call it good because we're well over time now. So Microsoft partners with quite a few vendors in the SaaS space, and we also offer solutions in that space as well. Our viewpoint on SaaS is that while there are products and features built into these products that will rely on the ability to kind of inspect traffic and determine what's going on with a given set of end user traffic at the network layer, that's really not the best way to actually gain insight into what that traffic is, or what the intent of the end user is. The right way to do that is to actually integrate directly with the SaaS solution and get feedback from the SaaS solution, on what's actually going on, and then take action. The reason for that is that what's actually in those network packets is constantly changing, and it's extraordinarily difficult for third parties, or heck, even for Microsoft with our own products that that we've acquired that attempt to do this at the network layer, to understand in a reliable way what's going on inside those requests, where Microsoft, from an audit logging perspective, or via other feedback mechanisms that we have and integration points that we have, can say, from the service side, this is the exact identity of the end user, this is exactly where they're coming from, and this is exactly what they were trying to do. SaaS solution, take action as you see fit. So the answer there is generally avoid the solutions that are proxying traffic and inspecting traffic in order to try and make those determinations, and instead look for products that are actually going to to integrate with the APIs that we have available to get that additional level of granularity. And ideally, you actually get a better result. Well, I won't say ideally, you will get a better result, because it's not going to be guessing or trying to keep up with things via reverse engineering. All right. So I will call it good there. Thank you so much for your time. Really appreciate all the attendees today, and looking forward to MEC coming back again, hopefully without as much delay. So thanks, everyone. Have a great day.